Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last lecture, we have studied binary addition and binary subtraction operations. Also, we talked about how subtraction can be performed using addition. In this session, we focus on multiplication, division techniques and how addition and subtraction is used for accomplishing multiplication, division operations. Binary arithmetic, multiplication and division. We start with binary multiplication. The basic process of multiplication is known to us, is it? The operators involved in multiplication are multiplicand and multiplier, and the result is the product. Normally, we use two methods for multiplication, one direct method and two partial product method. Actually, multiplication is repeated addition. In direct method, we add the multiplicand n times where n is the multiplier. That is, if you are asked to find 2 into 3, we will calculate the result as 2 plus 2 plus 2, but it is not feasible always. So, we go for partial product method, which we are very much familiar with. Let us multiply two number, say 23 and 14 using partial product method. In this example, which is the multiplicand? 23 and multiplier is 14. Okay, let us start. The least significant digit of multiplier, that is 4, is multiplied with 23 and the result is written, that is 92. This is a partial product. Then multiply the next digit of the multiplier, that is 1, with the multiplicand, and we write the next partial product 23 in the next line. Each partial product is to be written by shifting one position to left. Then add all partial products, we get the result 320. Therefore, 23 into 14 is equal to 320. As we are so familiar to this method, more explanation are not required. In the same way, we can multiply binary numbers too. Before we start, let us just go through the rules of multiplication in binary. That is, 0 into 0 equal to 0, 0 into 1 equal to 0, 1 into 0 equal to 0 and 1 into 1 equal to 1. In binary multiplication, we choose two integers m and q as inputs. The multiplicand m takes the form m equal to mn minus 1, mn minus 2, etc. m1, m0. The next, the multiplier q takes the form q equal to qn minus 1, qn minus 2, etc. q1, q0. Now, let us multiply the binary numbers 11001 and 10101. Let 11001 be the multiplicand m, whose decimal equivalent is 25, and 10101 be the multiplier q, whose decimal equivalent is 21. So, here q4 equal to 1, q3 equal to 0, q2 equal to 1, q1 equal to 0 and q0 equal to 1. In step 1, m into q0, that means 11001 into 1, we get 11001. It is the first partial product. Then in step 2, we obtain the second partial product m into q1, that is 11001 into 0, which is equal to 00000. It is 0. Likewise, we can find all the partial products. When we multiply with 1, we get the same number and otherwise 0. So, it is easy to find the partial products in binary multiplication. Next, m into q2, which is equal to 11001, the third partial product. Then m into q3 equal to 0, and we also obtain the fifth partial product m into q4 equal to 11001. The last step is to add all partial products. Before adding all products, we should shift each intermediate product to left according to their number as we write in decimal multiplication. That is, write q0, the first partial product 11001, then one left shift and write q1 00000, then 2 left shift and write q2 11001, then 3 left shift and write Q3 00000 and write Q4 after 4 left shift 11001. Adding all these partial products, we get the result as 100000101, which is equivalent to 525 in decimal. In binary, we have only 2 bits, and so multiplication can easily be done with the process of successive shift and add operations. This method of multiplication works perfectly fine. But as you know, several addition and multiplication operations are involved here. When multiplication is performed in decimal, we never bother about the number of digits appears in the result. But in binary multiplication, we have to, because ultimately it is to be executed in a hardware. The number of bits are already set. We cannot change it. When we observe multiplication problems, we can see that the number of bits required in the result is the sum of bits of multiplicand and multiplier. Means when we multiply two 4-bit numbers, the product will have maximum of 8 bits. So, we must establish the maximum size. No additional concerns when the numbers are unsigned. But signed multiplication requires special considerations for negative numbers, that is, when the numbers represented in 2's complement form. Just consider this example, two 4-bit numbers represented in 2's complement form, 1001 into 1010, that is minus 7 into minus 6. So, we expect the result positive 42, that is 101010. But when you follow partial product method, we end up with 10111010, which is undesired. So, this method fails with signed binary numbers. This can be corrected by extending the number of bits of both operands to the product bit width. That means, when we use two 4-bit numbers, we have to represent them in 8 bits, as the maximum number of bits in the product is going to be 8. So, let us represent each number in 8 bits. So, minus 7 is 11111001 and minus 6 is 11111010. Now, let us multiply them. Write the partial product only up to the 8th bit and see the result. It is 0, 0, 1, 0, 1, 0, 1, 0, which is equal to 42 to the base 10. Booth's algorithm. The next topic of study is Booth's algorithm for multiplication. It is used to multiply two signed binary numbers represented in 2's complement form. This algorithm was proposed by Andrew Donald Booth in 1951. He employed shift operations to create this faster multiplication algorithm. The algorithm operates on two facts. They are: first one, string of zeros in a multiplier does not require additions but just shifting. And the second one, string of ones in any binary number from weight 2 raised to I to weight 2 raised to j can be written as difference of 2 raised to I plus 1 minus 2 raised to j. For example, take the binary number 00111101. Here the value of string of ones from position 2 raised to 2 to 2 raised to 6 is 2 square plus 2 cube plus 2 raised to 4 plus 2 raised to 5 plus 2 raised to 6, which is equal to 124. It is the same as 2 raised to 7 minus 2 square, that is 2 raised to 6 plus 1 minus 2 square. In general, 2 raised to I plus 1 minus 2 raised to j. These concepts are followed in Booth's algorithm with the introduction of Booth multiplier recording. Anyway, we do not get into the details. Let us start with the process of multiplication. Consider two numbers m and q let m be the multiplicand and q be the multiplier. And let us also consider two storage elements q minus 1 and a whose initial values are set to 0. So, q minus 1 equal to 0 and a equal to 0. Actually, q minus 1 is to store the previous LSB of q. So, initially it is set to 0. Now, m is the multiplicand, q is the multiplier, q minus 1 initially set to 0 and a initially set to 0. Now, to proceed with, we need to examine two bit values q naught, that is LSB of q, and q minus 1. What should we do with these two bits? Yes, listen, here we introduce three cases. First one, if q naught and q minus 1 are same, that is if q naught q minus 1 is 0 0 or 1 1, then perform arithmetic right shift by 1 bit. Second point, if q naught q minus 1 is 1 0, then you need to perform a equal to a minus m and then arithmetic right shift. And the third point, if q naught q minus 1 is 0 1, then you have to perform a equal to a plus m followed by arithmetic right shift. These three cases reflect the Booth multiplier recoding. This process is repeated n times because Booth's algorithm calculates the product in n steps, where n is the number of bits used to represent the operands. Let us have a demonstration of Booth's algorithm, but before that let me just explain briefly what arithmetic right shift is. It is shifting a bit position to the right by retaining the MSB as it is. For example, let q equal to 1 0 1 1. Arithmetic shift right on q will give us the result as 1 1 0 1. In this algorithm, the arithmetic shift right operation is performed on the concatenation of a and q. The process of multiplication using Booth's algorithm can be more explained using a flow chart. Let us consider two numbers minus 7 and minus 6. 7 is 0 1 1 1, minus 7 is equal to 2's complement of 0 1 1 1, which is equal to 1 0 0 1. Then 6 is 0 1 1 0. So, minus 6 equal to 2's complement of 0 1 1 0. 1's complement of 6 is 0 1 1 0 is 1 0 0 1 plus 1, we get 1 0 1 0. In the first step, set the values of a, m, q, q minus 1 and n. A equal to 0 0 0 0, m equal to 1 0 0 1, q equal to 1 0 1 0 and q minus 1 equal to 0, and n equal to 4 because we use 4-bit numbers. Check the values of q naught q minus 1, it is 0 0. Now, refer the flow chart. When q naught q minus 1 equal to 0 0, go for ASR, that is arithmetic shift right. Before that, the last bit of q is to be stored in q minus 1, then ASR. When you apply ASR on current AQ, we get 0 0 0 0 0 1 0 1. Now, A contains 0 0 0 0, Q contains 0 1 0 1 and Q minus 1 is 0. The value of n is decremented by 1 and it is 3 now. Let us continue by checking values of q naught q minus 1, it is 1 0 now. So, we need to calculate a equal to a minus m followed by ASR. A equal to a minus m can be calculated easily as a equal to a plus minus m, a equal to 0 0 0 0, m equal to 1 0 0 1, then minus m equal to 0 1 1 1. Then a equal to a plus minus m, which is equal to 0 0 0 0 plus 0 1 1 1, that is equal to 0 1 1 1. This is the new value of a. Now, we have to apply ASR on current AQ and we get 0 0 1 1 1 0 1 0 1. By now, we completed 2 iterations. Now, the value of A is 0 0 1 1, Q is 1 0 1 0 and Q minus 1 is 1. Again decrement n by 1, as it is not 0, we continue checking values of Q naught Q minus 1, it is 0 1. So, go for A equal to A plus M followed by ASR. So, A equal to 0 0 1 1 plus 1 0 0 1 which is equal to 1 1 0 0. Q is the same, that is 1 0 1 0. Store Q naught in Q minus 1. After the arithmetic shift right, the values of A, Q and Q minus 1 are 1 1 1 0, 0 1 0 1, 0 respectively. Then n equal to n minus 1, that is equal to 1. So, we proceed. Check Q naught Q minus 1, it is 1 0. So, we have to calculate again A equal to M minus M, then ASR. A equal to 1 1 1 0 minus M is 0 1 1 1 and A equal to A minus M, that is calculated as A equal to A plus minus M, that is 1 1 1 0 plus 0 1 1 1 which is equal to 0 1 0 1 after discarding the overflow bit. Now, A equal to 0 1 0 1, Q equal to 0 1 0 1 and applying ASR we obtain AQ as 0 0 1 0 1 0 1 0. Then n is decremented, it is 0 now. So, we can stop here by recording the results as the current AQ value which is 0 0 1 0 1 0 1 0. Leading zeros can be dropped and we are left with 1 0 1 0 1 0 in binary, which is equivalent to 42 to the base 10, which is same as minus 7 into minus 6. So, Booth's algorithm is a more simpler procedure to multiply binary numbers represented in signed 2's complement form. This algorithm is very efficient in terms of speed and number of additions or subtractions required for multiplication. But when the pair of 1 0 or 0 1 occur frequently in the multiplier, Booth's algorithm will yield to a worst case implementation. Booth's algorithm performs less number of additions and subtractions than normal multiplication algorithms by implementing Booth multiplier recoding. The advantage of using Booth's algorithm is that it reduces the number of operations depending on the multiplier. Booth's technique is again modified to speed up the multiplication process. Bit pair recording was the technique for faster multiplication in Booth's algorithm. In this method, the multiplier bits are paired and assigned a new bit for each pair. That is how the multiplier was recorded. The table shown here is the Booth multiplier recording table. The first two columns shows the multiplier bits bit I and bit I minus 1 and the third column gives the multiplier recorded bit. And when the multiplier bits are 0 0, the recorded bit will be 0. When they are 0 1, multiplier recorded bit becomes plus 1. When they are 1 0, it is minus 1 and they are 1 1, it is 0. If the multiplier is 0 0 1 1 1 1 1 0, the recorded multiplier can be obtained by pairing them. Let us start from the LSB. We have to add a 0 at the right side. Then start pairing 0 0 we get 0, then 0 1 we get minus 1, 1 1 0 1 1 0 1 1 0 1 1 0 1 0, that is plus 1, and for the last pair 0 0 the recorded value will be 0. Now, the recorded multiplier is 0 plus 1 0 0 0 0 minus 1 0. Zeros in multiplier just requires shifting and no additions. So, the process becomes faster. Let me also introduce you one more method, bit pair recoding, a fast multiplication technique that reduces the number of summons to n by 2 for n bit operands. Bit pair recording. It is derived from Booth's algorithm. Both recorded multiplier bits are grouped in pairs and gives one recorded multiplier bit for each pair. This reduces the number of summons to n by 2, where n is the number of bits in the actual multiplier. The table given here shows the multiplier recorded bits. See, when the multiplier bits are 0, 0, 0, then the recorded bit is 0. When they are 0, 0, 1, the recorded bit is plus 1. For 0, 1, 0 it is plus 1, 0, 1, 1 it is plus 2, and for 1, 0, 0 it is minus 2. Then 1, 0, 1 minus 1, 1, 1, 0 minus 1, and for the last combination 1, 1, 1 it is 0. Let us consider the previous example again. We already completed writing Booth recorded multiplier. Here in bit pair recording, both multiplier bits are paired to obtain bit pair recorded multiplier. It is the same as pairing 3 bits from LSB. The first 3 bits are 0, 0, 1, and from the table we get the recorded bit as minus 2. The next 3 bits are 1, 1, 1. Its recorded value is 0. Again the next 3 bits are 1, 1, 1, and the recorded bit value is 0, and the last set of 3 bits 1, 0, 0 gives a plus 1 as the recorded value. Now, the bit pair recorded multiplier is plus 1, 0, 0 minus 2. The number of multiplier bits are halved. Thus, it reduces the number of summons by half. Thus, in order to speed up the multiplication process, the bit pair recording of the multiplier is used. It is used to reduce the summons. There are few more methods for fast multiplication which is not within the scope of our discussion. Anyway, all these techniques help in reducing the time for multiplication. The next topic of our discussion is binary division. First of all, let us look into division in decimal number system. Suppose we need to divide 142 by 3, decimal division proceeds like this. Leftmost digit, that is 1, of the dividend is considered, but 1 is less than 3. So, the quotient digit is 0. Then we take 2 digits together from left, it is 14, and so the quotient digit is 4. Multiply 4 and 3, we get 12. Subtract it from 14, the remainder is 2. Bring down one more digit from the dividend, then it becomes 22. Now, 7 3s are 21, so quotient digit is 7. Subtract 21 from 22, we get 1 as remainder. No more digits to bring down. That is the end of the division process. Finally, the quotient is 47 and the remainder is 1. Binary division is quite similar to decimal division. We follow the same procedure. To make it more clearer, let us take a binary division example. Suppose A equal to 1, 0, 0, 0, 1, 1, 1, 0 and B equal to 0, 0, 1, 1, and you are requested to divide A by B and get the result. Leading zeros can be dropped from both the numbers as they do not have any significance on this context. So, A can be written as 1, 0, 0, 0, 1, 1, 1, 0 and B equal to just 1, 1. Now, let us start. Suppose you need to divide 1, 0, 0, 0, 1, 1, 1, 0 by 1, 1. We follow the same procedure as we did in decimal. First, we start from the left of the dividend. Then find the group of bits from left from which the divisor can be subtracted. 1, 1 cannot be subtracted from 1 and 1, 0, and so the corresponding quotient bits are 0. Then we consider 3 bits together from the left of the dividend, that is 1, 0, 0. Write 1 at the quotient portion, then multiply and write 1, 1 here. The next is to subtract 1, 1 from 1, 0, 0. we get 1 as remainder. Then bring down the next digit from the dividend. So, the number becomes 1 0, but 1 0 is less than 1 1, and so we write 0 at the quotient portion and bring one more digit down. Now, it becomes 1 0 1. This is greater than 1 1. So, the quotient bit can be written as 1. Then multiply, subtract, and we get 1 0 as the remainder. This process is repeated until we complete all digits from dividend. And finally, we get the quotient as 0 0 1 0 1 1 1 1 and the remainder as 0 1. Each phase in binary division includes 4 different steps. They are: first one divide, second one multiply, third one subtract, and fourth one bring down. In the first step, we divide the working dividend by the divisor. There we get a quotient either 0 or 1. In the second step, we multiply the quotient bit by the divisor. This product is subtracted from the working dividend in the third step. And in the last step, we bring down the next digit of the original dividend to form a new working dividend. This is the process of division in binary. With this, let me wind up the session. I will summarize the topics we discussed. The objective of this module was to discuss different multiplication and division techniques used in binary. The focus was on multiplication as it is more important and popularly used in some of the digital circuits. Booth's technique for multiplication was detailed as it handles both positive and negative numbers represented in 2's complement form. We also had discussion about Booth recording multiplier and bit pair recording multiplier. In both cases, the number of multiplier bits are recorded to reduce the number of partial products. At last, we discussed the binary division technique. With this, I conclude. Thank you for watching. See you in the next session. Bye.